All right, let's get started. I have here some pictures that Mr. Fitzpatrick provided me. This is a threaded tension rod that is in a community center installation, and that is a pretty deflected rod. Because, I mean, just look at it. It's sort of, you know, that's me tracing it. Also, that's its connection. That's pretty interesting. No, that's the floor. Don't do that. That's all I'm saying. In all seriousness, though, we were talking about it for this installation. It's actually probably fine because now that the structure's up, the concrete wall is probably taking a lot of that lateral load. But somebody should look at it. So, but yeah, I just figured you'd get a kick out of that. All right, let's talk about some housekeeping, and then actually some literal housekeeping. So homework number 3 is due on Monday. I do want to make a note about the homeworks. So there's 48 people in here, and if I passed out all of the homework assignments to everybody, I'd be here for a while. So what I've done is I've started putting the homework assignments on the cart. If I gave you an assignment today, that wasn't homework number 2, that was homework number 1. So what had happened was it had been sitting on the cart for like over a week, and I was like, we got to get rid of these. So what I don't want to have happen is it's like April, and I've got like a pile of homework number 2, and then a pile of homework number 3 that's like stuffed under the wheel, and then homework number 4 that's like in between that little bracket on the column, and it's a mess. So what I'm asking is this. I'm going to put homework 2, so homework 2 is graded. The grades are posted. I'm going to put that on the cart after class. You don't have to grab it right now. You don't have to grab it, tomorrow or anything. But do me a favor and try and grab it within a week or so, because otherwise it's going to be a mess. 48 students. Imagine if there's 48 students and I have 3 homework assignments. It's 48 times 3. That's a lot. So so just do me a favor and grab those, at your convenience. I do have a couple things I wanted to mention on the assignment. All in all, I think y'all did pretty well, but there's a couple things that I think are worth mentioning. So like, and I just as an for instance. Okay, so let's take, for instance, problem number 3. Okay, so this is problem number 3, and we have, a series of bolts in this channel. Let me ask you a question. Are they going through the flange, or are they going through the web? So when you compute your net area, it's the web thickness, not the flange thickness, because the bolts, see, they're going through the web. And the reason I'm saying this is because there's going to be instances like that. There's going to be instances where the bolts are being connected in a different fashion. There's going to be instances where it's different, okay? And so what I don't want you to do is get into this mode that, like, this is what Dr. Michelson did on example 2B. So if I do this exact same thing on the homework assignment, I'll get 100, okay? And I'm just doing that to help you all out, I'm not trying to be a jerk or anything. I know this is the first time you've seen a lot of this stuff. I just make sure that you're paying attention to this stuff, okay? And this is just a for instance. Like I said, by and large, you all did great. I just wanted to point out stuff like that, okay? Because I know in this class, it's really easy to go, oh, the net area is this minus 4 DHTF. But it's not TF because they're not going through the flange, they're going through the web. So everybody okay with that? That's just an instance. So I have the solution posted. I'll have the hard copies on the cart outside my office after class. You all can grab them at your convenience. And yeah. Sound good? Any questions? Now, keep in mind, we're still, so in lecture, we're in exam 2 mode. We're talking about bolted connections. So I'm going to get back into it. Okay. So last time we had concluded our discussion on threaded rods, and we started talking about bolted connections. We're taking it a limit state at a time, and we're also going to look at bolt spacing and layout requirements here in a little bit. And if we have time, we might get into our first bolted connection example. So we left last time by discussing the concept of bolt shear, the idea of a bolt essentially shearing in half. And so our governing equation is just the nominal shear capacity times the area, and then our phi value is 0.75. Fortunately, we don't really have to use this equation very much because we have table 7.1. But what I wanted to do is I sort of wanted to recap this, and I wanted to discuss really the two primary issues to make sure everybody's clear with this. The two primary issues associated with determining the shear capacity of a bolt. That's number one, whether or not the threads are included in the shear plane. If you don't know, what do you assume? That they are included. So if you don't know whether or not the threads are included, assume that they are. Obviously, if you're shearing through the threads, you're shearing through less bolt. So the bolt capacity is going to be lowered. So when in doubt, make a conservative assumption. And the nominal shear capacities reflect that accordingly. Don't forget the naming convention. If I say group A-N, that means threads included. Group A-X, threads excluded. The second thing that we have to ask is whether or not the connection is in a single shear or double shear scenario. If it's in double shear, the bolt is twice as strong, not because the bolt magically got stronger, but because you have to shear through more bolt in order to fail it. So anytime you look at a double shear capacity, the capacity is double that of single shear. And like I said, we don't have to do a lot of this math because table 7.1 does it for us. So table 7.1 reports bolt shear capacities for single shear and double shear scenarios, for threads included, threads excluded scenarios, for group A and for group B, and for various bolt diameters that we're interested in. It does report in ASD and LRFD, but we don't have to utilize, or we're not utilizing ASD, so we're only using the blue numbers. Now, another thing that's kind of worth pointing out, if you turn the page in that section in the manual, there are actually a number of design aids right around there that are pretty useful. So for instance, the next page reports slip capacity. So we're going to look at that a little bit later. The page on the right reports tensile capacity of bolts. And so for instance, you'll notice that the tensile table is a bit smaller because whether or not the shear planes are there, or whether or not it's single shear or double shear, the threads are included or excluded, doesn't matter because we're not applying shear, we're applying tension. So all that matters is really the diameter. So pretty simple. Everybody good? All right. Now, this is where we left off last time, and so I kind of want to elaborate on this topic a little bit. So last time we were looking at failure of the bolt. Now let's look at the failure of the plate. So you have a plate with a bolt hole, and you have a bolt going through it, and so the bolt is actually bearing on the plate. It is applying force to the plate. And so there's two different ways that the plate can fail. The first is that the edges of the plate can basically fracture and sort of tear the edges of the plate. So we call that bolt tear out. And it's kind of similar to the fracture limit state, or similar to block shear. Because the edge of that plate is seeing shear, you're going to see a 0.6 value kind of indirectly pop up. Now, the other failure is what's called bolt hole ovalization. Basically, as the bolt bears on the plate, you can sort of get some localized yielding and plastic deformation, and the plate sort of bunches up there at the end. And so we have two different limit states that we have to check. We sort of use one equation, but it accounts for both. Everybody okay with this? All right. Now here's the equation. Now first off, if you remember the format of equations in the manual, if you ever see a capacity that's written as, the nominal capacity equals a pile of junk less than or equal to another pile of junk, that's basically just the manual's way of saying that it's the minimum of those two values. So Rn is computed as the minimum of this quantity over here on the left or this quantity over here on the right. I'll go ahead and tell you, really the only new quantity that you see in this expression is this term LsubC. Okay? Now I'll go ahead and forewarn you, there are different LsubC values whether or not you're looking at a bolt on the edge of the plate or a bolt within the interior of the connection. So because of that, you're actually going to have a different nominal capacity for edge bolts than you are for interior bolts. So you sort of have to do this calculation twice, and then you sum up the capacities to get the total RN for your connection. Now phi is 0.75. If you look this equation up in the spec, there are actually different expressions for whether or not you're considering deformation at the service load or not. We are going to consider that to be important. Because to be honest, I really think it's important to ensure that your connection geometry remains consistent. And so, unless otherwise noted, any structural engineer is going to do that as well. Other than that, you need the thickness of the material that you're going through. So if it was, let's say, that channel, the thickness would be T sub W, the thickness of the web. You need the bolt diameter, and you need F sub U. This is a fracture, essentially a fracture limit state. Everybody good? All right, like I said, we can write that as the minimum of these two expressions, and it's kind of nice the way the equation is written, because basically this pile of junk less than or equal to this other pile of junk where it's the minimum of those two values. Each of those two expressions refer to a given effect. So that 1.2 LCTFU, that's the one that relates to the tear out, to the edges of the plate ripping. Okay, and the 2.4 dBTFU, that's the ovalization. That's the plastification of the bolt hole. So each equation is relating to that particular effect. So basically the minimum one governs. So it's basically saying whichever one's going to happen first, that's going to be the governing capacity of that given bolt. So everybody good? All right. Now, the term that's new, the term that's unique, is this term LsubC. Okay? So I haven't really talked about LsubC yet, so I want to take some time and kind of define it. So LsubC is essentially defined as the clear distance between the edge of one bolt hole and either the edge of the other bolt hole or the edge of the plate. And so this image that you see here, this is going to kind of describe it pretty well. So what I have here is an image of a bolted connection, and I've got two bolts in it, just for simplification. And I've got a tensile load applied upward. Okay, so really what we're talking about is, the load going like this, and so the bolts are going to be bearing on this end, and so we're basically going to be talking about the plate failing in this direction. So LsubC, if you want a simple definition, it's a clear distance. It's a distance from edge to edge. So I'm going to introduce a couple terms. So this term S is the bolt spacing. I'm using the same terminology that we use for stagger factors. So remember, S was along the direction of loading. Okay? So S is from center of bolt to center of bolt. And L sub E, this is a new term. This is the edge distance. This is from that last bolt towards the edge of the plate to the clear edge. Everybody good? Okay. Now, so we're talking about clear distance. So if those are the spacing and the edge distance, these are the LsubC values. So because of your connection geometry, you're going to have two different LsubC values. You're going to have an LsubC value for your interior bolts. So again, this bolt is going to want to fail down here. So this is the clear edge distance that we're after. And this bolt is going to want to rip down this way. So this is the clear distance that we're after. So for the bolts that are on that far edge, the LsubC value, I'm calling that LsubCE, that's going to be the edge distance, and it's going to be minus half a hole diameter. Okay? Whereas for the interior bolts, it's going to be the bolt spacing. Then we're going to come in half a hole diameter, another half of a hole diameter, so it's going to be a single hole diameter. So we have S minus DH for the interior bolts, and for the edge bolts, it's the edge distance minus half a hole diameter. Everybody okay with that? Any questions? All right. Now, so if you can understand that, I think the computation of the capacity is pretty easy. Now, like I said, that first equation relates to bolt tear out. The reason why, if you look at the expression, it's actually kind of pretty easy to derive. This first expression, this 1.2 LCTFU, it's kind of like a mini block shear check, because if you were to think about this in block shear terms, what would be sort of the area along this section? Well, it'd be the length times the thickness, right? And in order to get a capacity, that's the area, so we would multiply it by some limiting stress, so we'd call it FU, but because it's in shear, we multiply it by 0.6, okay? But here's the thing, there's two of them, because there's one here and there's one there. So we take that whole thing and we multiply it by 2. So that's how you get 1.2 LsubC TFU. So there's really not a whole lot of magic or mystery to that expression. It's just making your life a little easier by doing this sort of mini block shear check, okay? Everybody okay with that? Now, this one you can't derive. That's just empirical, okay? That's just, you know, monitoring, you know, doing testing and figuring out a simple value that fits the test data. So there's no really super way you can derive that. So, or super accurate way, I should say. Everybody good? So if you look at this expression, notice how there are some terms that are common. So one of the things I can do is I can factor these out. So I can factor out the T and the FU, and I can actually factor out a 1.2 and make this expression a whole lot more user-friendly. I am sorry for another note on this slide, because you're not going to like me very much. Here's the thing. When we do bolt bearing computations, we are actually evaluating the physical dimensions of the hole. We're actually looking at the hole as it is and computing its capacity. Let's go back to tension members. How do you determine the diameter of the hole? You add 1/8 of an inch, but why do you add 1/8 of an inch? We added a 1/16 twice, right? Now why did we add, let's pop quiz. Give me the reasons why we added those 16ths. There was 2 reasons. We added 1/16 for one reason and 1 for another. Okay, so one of them was erection tolerance. So you actually had to drill the hole a little bit larger to fit the bolt in. What was the other one? The error, you're basically saying the same thing. But let's talk about that damaged material check. What we were saying is that little bit of ring of material, how effective is it in transferring stress to the entire member? Okay? All right? So that was sort of an analytical add-on that we did for the tension member evaluation. We're not looking at tension members right now. We're looking at the physical dimensions of the hole. So when you're doing a bolted connection bolt bearing check, you don't add 1/8 of an inch. You add a 1/16 of an inch. So, like I said, I hope you don't hate me too much, but that's just steel design. So, any questions on that? Again, we're actually evaluating the physical dimensions of the hole, and the actual hole is a 1/16 of an inch larger, not 1/8. No. So here's the actual bolt. When we drill the hole, we drill it a 1/16 of an inch larger. The actual hole is a 1/16 of an inch larger. Here we're evaluating the actual hole. When we did tension members, we added another 1/16 because we said that little bit of material around the hole wasn't very effective in transferring stress to the whole member. But we're not evaluating the whole tension member right now. We're looking at the bolted connection. Everybody else, does that make sense? Okay. All right. Before we start getting into example mode and capacity mode, we got another big question that we need to answer. And I got this question, I think, a few lectures ago, and I said, we'll get to it. Well, now we've gotten to it. And the question was, why are the bolts spaced at 4 inches? Why aren't they 3? Why aren't they 2? How do you figure out how far the bolts are far from each other or far from the edge? That's what we're going to do now. So one of the things that you need to be able to determine when you're designing a connection, I think it's pretty easy to determine the required number of bolts. You got 100 kips on a connection. Each bolt can hold up 20 kips. How many bolts do you need? 5, right? Just 100 over 20. That's pretty easy. But What we haven't answered yet is, okay, you got 5 bolts. What do? Just put them wherever? Now, how do you lay them out? How do you properly detail a connection? And so what we really have to address are 2 requirements. We have to address bolt spacing requirements, how far apart bolts should be spaced from each other, and edge distance requirements, how far apart bolts can be from the edge. Now, if you want the general reason why these limits are even there in the first place, there's 2 reasons. One, they're meant to facilitate construction and to prevent corrosion. And that'll become clear here in a second. So let's take each of these one at a time. So first off, we should be looking through Chapter J. So I want everybody to grab this lovely steel manual. Let's go to Chapter J. We're on 16.1-130. Has everybody brought their AISC Steel Construction Manual, 15th edition, the one with the turquoise blue cover, right? Oh my goodness. Okay, so just so you're aware, the way that Chapter J is organized, we're in Section J3. J3 is on bolts. So what do you think J2 is on? If J3 is on bolts, what's J2 on? What's the other type of connector that we use? Welds. My goodness. All right. Chapter J4 is looking at the strength of connected parts. We'll look at that later. So let's go to J3.3. And if you notice, you can start seeing the sections move on because there's one on minimum spacing, there's one on minimum edge distance, maximum spacing, and so on and so forth. So let's look at minimum spacing. So the absolute minimum spacing of a bolted connection is, between 2 bolts is defined as 2 2/3 times the nominal diameter. It's actually a preferred spacing on the user note on the bottom is 3 times the diameter. I will be sure to tell you in homeworks or exams which one I want you to use. I'm not going to make it vague. But if I didn't tell you, what do you think you should go with? The preferred, right? Now, let me ask you a question. Why do you think that there is a minimum bolt spacing requirement? Who cares if bolts get too close together? Why? There you go. If the bolts get too close together, they start clanking together. You can't tighten them, right? They have to be at least some distance apart so you can at least put the structure together, right? So that's why we have minimum bolt spacing requirements, okay? To facilitate construction. Yes? No. That's a great question, and the answer is no. This is just laying out connections in general. Because whether or not we were talking about the direction of force or not, it wouldn't change the core issue that if the bolts got too close together, you couldn't tighten, you couldn't put a wrench around them. So that's a good question. Yes, yes, and yes. I don't, one of you. Okay, I guess you're going first. What? Well, but wait. Well, I guess I'm confused how you're tying the two together because bolt shear capacity has nothing to do with its spacing. I mean, how do you determine the how does it have to do with the yielding of the steel? The yielding capacity is 0.9 FYAG. I mean, I'm trying to understand, but I mean, well, that's a good question, and so you're going to check both. And if your bolt tear-out capacity is too small, then you might increase your spacing a bit. But in general, it's a reasonable discussion. In general, you would want your bolt spacing to be smaller rather than larger. And here's why. Okay, so here's a member, right? here's the end of a member. Okay, and here's the end of another member. 4 bolts, right? 4 bolts. So 1, 2, 3, 4. 1, 2, 3, 4. Now I space these out a lot further. The problem is that this bolt is going to be connected to something. So if it's connected to, let's say, a gusset plate, this plate only needs to be this big, whereas this plate needs to be that big. Bigger plates, right? More steel goes into the connection. So in general, I'd like to lump those bolts together as closely as possible. Now, I still have to meet bolt bearing capacity checks. So if I lump them as close together as humanly possible, and I'm going to have a problem with bolt bearing, then space them out a little further. That's exactly right. But, so I guess the core point I want to make is that bolt layout requirements and bolt bearing checks are independent of one another. You have to do both. So, did that sort of answer your question? Everybody else okay with this? Yes? Yeah, you would. If you increase the spacing, your block shear capacity would go up as well. So let's keep in mind, you know, these bolted connection checks that we're talking about, they're additive. We're adding on top of all the, you know, gross section yielding, net section fracture, and block shear rupture. So if you increase your spacing, it would affect that as well. So this connection is going to have a higher block shear capacity than this one. Absolutely. Absolutely. Anything else? This is good stuff. Now, let's extend this a little bit. I'm going to skip the edge distance. I'm going to get back to it. So let's take money and assume that it's Scrooge McDuck time and we have the pool full of coins that we can swim around in. Let's space our bolts out 20 inches from one another. We wouldn't have a problem with block shear or bolt bearing or anything like that, right? So why don't we do that? Take money, put money off to the side. Let's say we got piles and piles of cash. Why wouldn't we do that? Why wouldn't we space our bolts out super, super far from one another? But let's take money out of the situation. Let's say we got money for that plate. You're right, but let's take money out of it. Let's say that's not an issue. What do you think a bolted connection is designed to do? A bolted connection is designed to take plate A and plate B, connect them together. So what happens if those bolts get too far apart? Well, not enough friction, but let's say we're not dealing with a slip connection. But think that might happen? They might have a little bit of a gap between those two plates. Why is that a problem? Water. Water could seep in between the bolts. Water doesn't like metal very much. They tend to corrode. So there's a limit on the other end as well. Not only can bolts not be too close together, but they can't be too far apart. If they're too close together, you can't get a wrench around them. If they're too far apart, you're going to get water in between your bolts or in between your plates, and that's a problem as well. So just so you're aware, we have maximum spacing requirements and edge distance requirements because of corrosion. Okay, so let me go back and sort of recap everything. So minimum bolt spacing, that's 2 2/3 times the bolt diameter. A preferred bolt spacing is 3 times the bolt diameter. Minimum edge distance requirements, that's a lookup. And the reason, I mean, there's a pattern. You know, for the most part, it's you know, you take the bolt diameter and you add something like 1/4 of an inch. Although if your bolt diameters get kind of large, that pattern doesn't quite hold. The reason why it's tabulated and the reason why there's not a very pretty formula is because this basically comes from the fabricators. The folks who are using the CNC machines or the mag drills and whatnot and actually, you know, fabricating these holes. This is basically about the stretch of their comfort level. They don't want the bolts too close to the edge because they don't want to be drilling the plate and then, you know, deform the plate. So this is about as close for comfort as they want. This comes from the fabricators. And so this is a lookup. And so this would be so this is the minimum spacing requirement. This is the minimum edge distance requirement, how far the bolts are from the edge. And again, this is independent of the loading direction. It doesn't matter. We're not talking about loading at this point. We're just talking about fabrication. As for spacing and edge distance, so for edge distance, there's just a single limit. It's either 12 times the thickness or 6 inches. And that's just, you know, that's a corrosion issue. However, for spacing, it's a little more refined. The spacing limit on the maximum side is a function of your coating option. So for instance, if you have an unpainted member, the limits are a little more stringent. Whereas if you have a painted member, you're allowed a little more flexibility. However, honestly, in most real-world connection applications, if you're connecting member A to member B, that's not an issue. Usually, you'll be able to detail a connection and not have to worry about S-max. The only time that S-max, I would say, becomes a real big issue is if you have like a bolted cover plate on a beam. Then you really are wanting to try and use as few bolts as possible, so you're wanting to try and space them out. But that's a pretty rare application. Everybody good? If you want to put a nice little star in your notes on slide 172, I made your life a little easier. I put you a nice summary of relevant formulas and equations because I'm such a nice guy. So let's summarize this out. So bolt shear capacity, you don't need to compute that. You just look it up. It's just table 7-1. You should have a star in that or a tab in that on your manual. Bolt bearing, it's a pretty simple calculation, but you're going to have to do it a couple times because you're going to have you potentially are going to have a different bolt bearing capacity for edge bolts as opposed to interior bolts. The reason is because your edge distances are different. So LCI is S minus your hole diameter, and LCE is the edge distance minus half the hole diameter. And then how do you get the hole diameter? It's the diameter of a bolt plus a 1/16 of an inch, not an eighth. And your phi value is 0.75. As for layouts, we have bolt spacing requirements. We have S min and S preferred. This is S max. If you're evaluating a connection, just use S min and S max because the connection is what it is, so does it meet minimum and maximum requirements? Edge distance, it's just min and max. So pretty straightforward. Any questions? All right, so here's the problem we're going to do. I got a connection. I'm yanking on it essentially like this. I am going to be evaluating the ultimate capacity of this connection. So I'm using 1-inch diameter A325 or Group A X bolts. So that means the threads are excluded. It is, well, I'm going to let you all figure some things out for the capacity. But I've got a series of dimensions laid out right here. The bolt spacing is 3 inches in either direction. We've got some edge distance requirements we're going to have to check. So yeah, let's just get right to it. Anybody have any questions? That's a good question. I generally just put a tab right in chapter J3 because there's a lot of different tables here worth checking. But that's what I did. It's not totally necessary because you could just write that stuff out on a formula sheet, but I think you should have something there. Okay. Give me a sec. Come on. There we go. All right. So let's compute a couple things right now. So just some standard info. So all right. We know that the bolt diameter is what? 1 inch. So that means that the hole diameter is what? 1 1/16. So just go ahead and handle that right now. Now we know that this plate, or that both of these plates are fabricated out of what? A36. Yeah, I was erasing that. So whenever you're doing bolted connection checks, for the most part, you usually only need an F sub U value. Now, I'm curious, without looking it up, anybody remember what this is? It's 58. After a while, a few of these you just kind of memorize. Okay. All right. So the way I'm going to handle this is we're going to keep this simple. Let's handle bolt shear first. All right. So I told you it was group A X bolts. The diameter of the bolt was 1 inch. And you tell me what's going on with the shear situation. Somebody else, somebody over here. All right, I'll walk through. Is it single shear or is it double shear? There we go. There we go. So with this information, I want you to tell me what that is. What is PRN for a bolt? For a single bolt. $80.1. Now what table is that? Now, I want to make sure that everybody else can find that. So I'm going to wait for a second. I want to see everybody find that on their own. I see a few folks still haven't gotten there. Those tabs are starting to get pretty valuable, aren't they? Everybody able to find it? So let me pull this up here. Hold on. So here's the table. So we have group A, X, and we're in a double shear scenario over to a 1 inch bolt. And so we're looking at this value right here. So, no. It's group A, and then the X means it's threads excluded. So it's either going to be group AN or group AX, or group BN or group BX. So it's not through X. It's a group A that bolt that is excluded. So, and it's double shear, and so we're looking at this row right there, and then it's 1 inch. So that's how we're getting the 80.1s. Everybody else okay with that? All right. No, that's fine. So, therefore, what is the actual capacity of the entire connection? What do I do with this number? I promise this isn't a trick question. I mean, what do I do with that number? Multiply by how many bolts you have. And how many bolts are in this connection? 6. 80 kips per bolt, 6 bolts. There you go. So I promise this is not a trick question. But in all seriousness, everybody good with this? Any questions? All right. Okay. Now, let's talk about bolt bearing. Okay. Here's the thing with bolt bearing, and you're not going to like this, but it's the facts. Whenever you have a connection, especially a connection like this where it's a shear connection. Does everybody see what I mean by shear connection? You got plate A, plate B, and you're loading it. So they're shearing against one another. Okay. Whenever you have a connection like this, you really have effectively, quote unquote, two members. You have the members that are transferring load that way, and then members that are transferring the load that way, like the hand motions. Okay, so really when you do your bolt bearing checks, you kind of have to check both. Okay, so what we're going to do is this. Okay, we'll walk you through the center plate computation. Okay, so what I mean by that is, let's look at our connection. Okay, so what are the plates that are transferring the load this way? Well, there's just a single 3/4 inch plate transferring load this way. What about the plates transferring load this way? Well, there's two 1/2 inch plates transmitting load this way. So here's sort of what's going on. All right. So I'm going to say that there's case 1, which is, we'll call it the center plate. And we've got case 2. We'll call these the splice plates. Okay. Now there's a couple different ways of going about this. I'm going to show you what I think is the easiest way in terms of bookkeeping. Okay? Now let's look at the center plate. I'm going to draw out the center plate. Okay, so it looks kind of something like this. Right? We have 1, 2, 3, 4, 5, 6. Okay? Now with the center plate, we're transmitting load this way. Okay? So whenever that's the case, the edge bolts are the ones that are on the far end. Okay? In other words, when you're yanking on the plate this way, these are the edge bolts. Okay? Because how is the plate going to want to rip? Well, it's going to want to rip like this. Okay? So these are the ones that are closest to the edge. All right? So help me out in terms of dimensions. What is this dimension right here? Say it again. It's 2.5. Look at your schematic. This is the dimension we're after. So this is 2.5. It's not this one. Okay. So this is 2.5. This is 3. This is 3. Okay. So for this case, this is what I propose. I propose that the bolt spacing is 3 inches. I propose that the edge distance is 2.5 inches. And I propose that the thickness is 3/4. Okay? That's what I propose is going on with this case. So if you're following along, help me out. What do you think the case for case 2 is? What do you think the bolt spacing for case 2 is? It's 3. It's the same, right? It's 3 inches. What is the edge distance? 2 inches. Now for the thickness, we have 2 ways of doing this. We could compute the capacity of a single plate and multiply it by 2 at the end. What I do, I just say that the thickness is that. We'll take a look. So we're looking at the cover plate, so we're looking at these top plates. Okay? So this dimension here, that's the 2.5. That's the main plate. But the cover plates, that's a good question. So the cover plates, these are the edge bolts. So how far is it from here to here? It's the 2 inches. Everybody okay with that? All right. Okay. Is everybody okay with how I came up with these boxes? Now, let's say, I want everybody to pay attention up here. So let's say, for the sake of discussion, that, let's just say for the sake of discussion, actually, let me use a thicker one. Let's say, just for the sake of discussion, this is a hypothetical. This isn't the case, but let's say it was. Is there any real reason, if that was the case, to even evaluate case 2? If that was the case, they'd have the same bolt spacing, the same edge distance, but this would have a thinner plate. So is there really any reason to check this one? Which one's going to be the worst case scenario? It's going to be this, right? So if the edge distances were the same, there'd only be one difference. It'd be pretty easy to look, because they're both made of the same steel, right? It's all the same steel, so all you'd have to do is take one look at it and go, I don't even have to worry about checking case 2. There's no point. I know this is going to govern, so move on. But unfortunately, that's not the case here. We have 2 different varying dimensions. We have a different thickness and a different edge distance. So unfortunately, we got to do the bolt bearing calcs for both of them, okay? We are going to reserve those bolt bearing calcs for next time, because we're running out of time. So that's all I got. I will see you all on Friday. Hey, after this, I'm going to put the homeworks on the cart. You don't have to grab them today, but do me a favor. Let's say by this time next week.
Is that going to be the same deal with mine, Cynthia, later?
Yeah.